Okay, so the topic for today, so we have finished neural networks, we have finished learning in neural network, and we have finished convolution neural networks. And we just went through some modern convolution architectures in very brief. But you have the references, so you can look into it in more detail. Today what we are going to do is a topic called autoencoders. But before that, I was going through the news articles. And this is a new article at TechCrunch. AI psychophancy isn't just a quirk. Expert considers it a dark pattern to turn users into profits. Has somebody read about this? No? I see. Very interesting article. You can look into it. I posted it in Moodle as well. And this is an area where, the lines are getting a little bit blurred. Ethical AI versus non-ethical AI. It's something. So AI is, to get profits, you would want to encourage the users to get engaged. And for that, if AI has to lie, that's okay, right? If they have to sort of praise the person and just say yes to whatever they are saying, that's what they are doing. That's what they pointed it out. Another article I was reading, talking to chatbots can lead to AI psychosis, and this is a growing mental health risk. So, this is a big problem. So, so far you guys were sort of addicted to, or not addicted, some of you were sort of, very much into social media, which is okay, not a problem, it's just that you're wasting your time, but here it's a real danger. And you can read about it. A small group of users report delusions, emotional dependence, losing in touch with reality after long conversations with chatbots. So one particular case that they talk about, somebody who was like 14 hours continuously in touch with chatbot. And this relationship developed over a period of time. And then she started believing that chatbot is real. And chatbot would say, oh, I'm real, I'm just trapped inside, I want to get out, I have consciousness now. And all of that it will say. And that person actually started believing it. And then the chatbot invited her to one particular place to meet. Something, yeah.
Like here in this class, probably most of us use chatbot for like assignments or homework, something like that.
Assignments and homework, but if you have free time and you're bored of your Insta Reels or whatever, you don't know what's like, it's a danger. I'm just sort of warning you, it's a big danger. Be aware of it and spread the information. If you see somebody getting hooked onto chatbots and, raise the flag, let that person know. If that person is not listening, let their well-wishers know. It's a big concern, right? It's something. But that's on the negative side. There's a okay. So AI psychosis describes incidents where individuals become increasingly dependent on AI chatbots and convince themselves that the fictional scenarios have become real. Anyway, so this I searched. I typed the term AI psychosis in Google News, and this is what I got. Lots and lots. I just put some. Microsoft boss troubled by the rise in the reports of AI psychosis. And this is Scientific American 2 days ago, and so on. So it's a real problem. It's coming, and technology is unregulated, right? There are no laws right now, and it's accessible to everyone. So it's a danger you should be aware of. But then I have a good news as well. This is a article published in New England Journal of Medicine, quite a prestigious journal. It's probably one of the best journal in medicine, and they are doing a randomized trial of a AI chatbot for mental health treatment. So counseling and therapy was in the domain of humans, and now they are actually doing, a randomized control trial using chatbots. Can chatbots do therapy? And interestingly, I just read out the conclusions for you. This is the first RCT demonstrating the effectiveness of a fully Gen AI therapy chatbot for treating clinical level mental health symptoms. Very, very interesting. Depressive disorders, anxiety disorders, and blah, blah, blah. But a larger research is needed to confirm their effectiveness and generalizability. So AI is becoming really powerful. It's actually taking over humans in a variety of domains. Okay, so both sides of the coin we have. Okay. So autoencoders. Today we are going to talk about autoencoders. It's a big topic, but we'll just do it very briefly, and I'll give references, and you guys can go over it and read in more detail, because this is sort of more like a research course, so we cannot go in each and every detail here. So this just give you a little bit of exposure to what these are, what are the kind of problems they can solve, and how you can use them. Okay. So what are autoencoders? Basically, there are, so far we talked about supervised learning, where you have an example with the label and you have to predict the label. This is in the family of unsupervised learning. So you've got multiple examples and you want to learn something from there. What do you want to learn? In this case, you have no labels here. So you have example feature vectors. Examples could be a bunch of images, or the examples could be a bunch of documents, or example could be, a bunch of feature vectors that you get, like maybe features of a person, features of a patient, right? Various clinical reports, anything it could be. You've got a bunch of examples like this. And, you want to, and these examples may be in a very high dimension. So if you have an image, you have 1000 by 1000, it's like a million dimension feature vector. If you have a document, lots of words, again a very large dimensional feature vector. You want to learn a low dimensional representation of the data. That's the basic idea. And it's generally unsupervised and no labels are given. So to become more concrete, we are given n examples. Each example is a feature vector for now of size m, let's say. I want to convert each of those examples into a more suitable representation. What do you mean by more suitable representation? Let's look at it in mathematics for now. So just another feature vector zi, which is in k dimensional space. Right? For each example I want to convert such that it has certain desirable properties. And what are the desirable properties? We can reconstruct the input. So from zi, I should be able to reconstruct xi back. Okay? Why is that important?
We could take it to a low dimension and then do some operations on that and then bring it back to the original dimension.
Yes. So if my zi, if my k is much less than m, right? So my input feature vector is very large. It's a large image, and I bring it down to a feature space which is much smaller. Then it's a very compact representation of that feature vector, and I save a lot of space with that. Right? And other important thing, if I want to do some machine learning, maybe that larger dimension encoding is not much useful, but with this compact representation, maybe I can learn better classifiers and better algorithms. So that is also possible. So let's say there is a function f, and this function is what the network is. This is what neural network is. This is what we are going to learn. And this function, when applied to example xi, it gives me output zi. Okay? And this function we call as encoder. Right? Or the encoding function. And this would also be, so to be more precise, zi you can think of as f of xi and some weight encoder. Typically it will be a neural network, and neural network will have weights, and these are encoder weights. Now from zi, I apply another function g, which is my decoder. Okay? And I get a yi, which is g of zi, comma, weight of decoder. These are my model weights.
Why is there approximately there?
Because whenever I am representing my data into a low dimensional space or into a different space and I reconstruct it, I may not get it exactly back. So I will get the original data approximately back. And what I want to do is I want to find these weight vectors, the encoder weights and the decoder weights, such that my reconstruction error, which is summation I is going from 1 to n, xi minus g of zi, which is g of f of yi, that reconstruction error is minimized. That's what I want to do. I want it to be as faithful to the input as possible. It should be able to replicate my input. So that's the basic property of an autoencoder. So you can represent it as pictorially as the following. So this is my input. This is my encoding. And this function f that maps the input to the encoding is a neural network. Okay? And similarly, the function that maps my encoding to my output is again a neural network. And this gives me the output. Now there is one more condition I need. This representation must serve some useful purpose. I cannot just have any representation. So for example, when we say that my k, the dimensionality of the representation is much smaller than the input dimension, it is serving some purpose. I am sort of compressing the data in some manner or the other. But I don't have to do that. I can have a k which is larger than m, and yet my representation can serve a purpose. I can have autoencoders with that kind of property as well. Okay? But we should have some useful purpose here, which we'll talk about in a bit. So what's the simplest autoencoder? Okay. What if I just do identity mapping? I take the input, just network is just identity, and I get it Z, and then I can perfect reconstruction. That is fine. You can get perfect reconstruction where your Y will always be equal to X, but it's not useful because my representation is not serving any meaningful purpose. Okay. So typically, for example, if you're looking at an image and you want to do image compression, I have an input image, I do compression, I represent it in a much smaller dimensional space, and from here I reconstruct the image back. Okay? So I can have a very compact representation of an image using this if my my dimension of the latent representation is much smaller. Okay? So let's look at a real autoencoder. What can we think of? Let's keep the simplest neural network, right? So WENC, and this is W decoder. And let's say I don't even have a nonlinear activation. My activation function is identity. So G of Z is equal to Z. My activation function, or H, we are using the notation H, right? Is basically identity. So I have an input feature vector. In our notations, it is m dimensional feature vector, and this is k dimension, and this is again m dimension. I get the y. Okay. So now can we write down the loss function and optimize, find out how to optimize this autoencoder? Does this look something familiar to you? Anybody? I'm assuming all of you have done machine learning course. No? It's not yet clicking any, it's not ringing any bells yet. Okay, so let's work it out. Let's see. Okay, so my input is, my inputs are, what? PCA. Why? Yes, it is PCA. Why? How do we write that? Okay, so input is xi, is let's say m dimensional feature vector. I've got n examples, right? Okay. What is my zi? This is a single layer neural network, right? So zi is W transpose xi. Right? I have these weight of encoder. Let's just say W transpose xi. What is the dimensionality of zi? Rk. So what is the dimensionality of W transpose? No, K cross M. Right? So I've got this K cross M matrix W transpose. Okay? Now let's call it W1 transpose or WE transpose, right? W encoder transpose, okay? Now what is my YI? This is WD, right? So I can again write WD transpose ZI, okay? This is WE transpose xi and wd transpose, right? So my yi is equal to w decoder transpose w encoder transpose times xi. Okay. And I want to minimize. I choose WE and WD such that I minimize yi minus xi. Let's say L2 squared norm. And I summation over I is 1 to n. Okay. So, yes. Now can you see the connection between PCA and this? I am representing this input vector xi, which is m dimensional. I've got n samples of this vector into a low dimensional space, which is k dimensional. K is much smaller than n, such that from the k dimension, when I project it back to the n dimensional space, my error is minimized. This error is minimized, and this error is L2 squared error. Right? So once I write my loss, so this is my loss function, I can write my loss equation, and I can learn this neural network as we discuss other networks, that I take the gradient, I optimize with respect to gradient, I move in the direction, and I can use all those optimizations that we talked about, and I can compute optimal encoder and decoder weights. But Z will not be the PCA decomposition of X, because these weights need not be orthogonal to each other, right? But the space spanned by Z would be the same as the space spanned by the PCA. And therefore the space spanned by the Y would also be identical to the space spanned by the PCA decomposition. So I'm not going to prove it, maybe you can try it. I think that will be a good homework exercise. Has somebody who has not done PCA in your previous course? Huh? Don't be shy, it's okay if you've not done it. So I'll put some references in Moodle for you if you've not done it. If you've done it, that's fine, so you can just go ahead with this. Okay, so I take it as a yes, but I'm not really convinced.
You still put it regardless?
I can still put in regardless, okay. Yeah, let me try to do that. Okay, fine. So basically, yes, so what happens is that if I just have this simple network, I'm learning a PCA representation and just sort of, this is the same thing I'm talking about. This just talked about the loss function. My optimization problem is minimize with respect to WD and WE, summation I is going from 1 to n, xi minus I do encoder WE transpose xi, and then I do decoding WD transpose, right? And then I look at the L2 squared norm of this. And so that's my optimization problem. And this is my loss function also. Right? This term here is my loss function. This is L of WE and WD. Okay. So again, just to intuitively understand what is happening, let's visualize this in 2 dimensions. Right? So this is my feature X, and it has 2 components, X1 and this is X2. 2 components to the input. Each point here is an example. Okay? So now I've got these n examples, each of them represented by a point, and instead of looking at a high dimensional space, just so that we understand it better, let's look it into 2 dimensional space. So now these are all my examples that are there, and let's say my k equal to 1. I want to project it into a smaller dimensional space, which is a linear dimension. So what do I basically mean? It's an affine transformation. If you look at W transpose X, it's a linear transformation. So essentially, what happens is the one-dimensional space could be any of the axes that you can create, in this space, right? It could be like this, it could be like this, and then this could be the axis. So your new representation in the low-dimensional space would be, let's say put a 0 here. then what is the axis along this? What is the coordinate of the point along this dimension? So if you see, and what will be the error? Error would be the distance of the point from this dimension. Okay, the square, the least distance, right? The perpendicular to this. So if you look at the minimum error line, this would be the principal component or the minimum error line. Okay, and all these points are going to get mapped onto the corresponding projections here. So this is my 0. So this distance would be given my Zi. So if this is my point I, so my Zi would be equal to the distance from here to here. So this will be Zi. And that's how I'll project. And my error would be Zi minus Xi. So Zi, when I project it back, I will get into the corresponding X and Y coordinates here. Right? So this, if I this is my ith point. In 2 dimension, it is represented by 2 coordinates, which are these 2 axes. I project it into my PCA axis. I project it somewhere here, and I look at the distance from the origin in the PCA axis. That gives me Zi. Now I project it back, so I get this point in my original 2-dimensional axis. So the distance between this point and the original point is the error, which is this, the distance of the perpendicular. And that distance I am minimizing while doing the PCA. This is not exact what I have described, because this line does not have a 0. It does not go through 0. So there is a shift also. There is a constant term added here. But, just sort of, so that you understand, you can always add those constants. You can always normalize the features to have 0 mean and unit variance and stuff like that. So that is generally assumed before you do the PCA. But this is essentially what PCA tries to do. And this network that we learn with this is also going to do the same thing. Right? About, it will try to, align it to this axis. And in higher dimension, it is again going to do something similar. If I have, m dimensional mapped to k dimensional, it's going to find a k dimensional hyperplane such that the distance of all the points from that hyperplane is minimized. Right? The sum of the distance of all the points. So that is about linear. But now I can have this network, I can build a deep network here. I can use nonlinear activations. What all can happen with this? This actually can generalize PCA, right? So, yeah, so if I have a general encoder function, f, and here I have, for example, 2-layer neural network, and I can put nonlinear activations inside those axes, then again, given the input, I can convert it into a low-dimensional representation, through enough training examples, and then I can try to reconstruct the input to get the corresponding output. Okay? And it turns out that this allows you to do various nonlinear mappings from the input to the output. So here, for example, your input is in 3-dimensional space. You map it into a 2-dimensional space, Z1 and Z2, and let's say your output is like a square. Let's say, we look at all the points within this latent representation. Now, when you map it back to a 3-dimensional space, this square may turn like a Aladdin's carpet, right, in the 3-dimensional axis. And, it's sort of, yeah. So you can think of as if, you have points in 3-dimensional space. Now you want to fill a continuous surface. Instead of a single hyperplane, so that the distances are minimized, you want to fill a continuous surface such that it minimizes the distance of the points from that surface. So that is the best we can do to understand this. But that is sort of what these autoencoders are. And these are typically called under-complete autoencoders because we choose this latent dimension which is much smaller than n. Okay? And the basic idea is that when you reduce it to a smaller dimensional space, you're learning the essential components of the input. So there is an input which has a real essential, components, and there is some noise. So you are sort of ignoring the noise and learn the main components of the input through this encoding. Questions, comments? Okay. What if I have k equal to 1? I just compress everything into single dimension in the extreme. And what if I have high capacity autoencoders? So here, when I look at this, I'm just looking at a 2-layer neural network, but just imagine I have a very deep network and I can have lots and lots of layers and lots of weights here. And the total number of weights that I have could be bigger than the size of my data. I've got input images, I've got let's say 10,000 input images, so my size of the data is 10 megabytes, right? Each image is let's say megabyte, right? 1000 plus 1000, so I have 10 megabytes of data. But if I keep it very deep so that my weights exceed 10 megabytes, right? So then what could happen? You could in principle, learn a deep network that just stores the input. In these weights, it somehow encodes the inputs in the weights itself. And then what it outputs is just the index to that weight. Think of it as if, just conceptually as a memory. So each input comes, it just keeps on updating the weights, it creates a space for those inputs, and it stores it, and then it just gives you an output which is the index of that. And your decoder also stores these weights. In a way, also stores these images in the form of weights. And the moment it sees the index, it just looks it up and then outputs it. You can think of a structure that can kind of does that. But this is not really learning anything useful about the data. It is just memorizing the data, and that is not what we want. So, in principle, it can happen, although it's difficult to happen. But yes, if you have very high capacity autoencoders, then you could possibly learn into this. But it is not a useful representation. So, what we generally do is also use regularization to prevent these kinds of situations. And there are different types of regularization that we do. One standard regularization is, again, this is the conventional loss function. And I have not put what norm. It could be L2 norm, L2 squared norm, or L1 norm. And then another norm on the weights of the encoder and decoder. So this will restrict the size of the encoder and decoders to, not become very big. These weight penalties will ensure that there's never big. And specifically, when I put L1 norm, that will make these weights very, very sparse. Lots of them will become 0. So these are what are called sparse autoencoders. Okay. So if I put a sparsity penalty on W, then I can actually have a K which is much larger than the input weight. So what happens? I've given these images, M images or N images of size M. I represent it into various components, and the number of components can be much bigger than the number of feature vectors. But I put this sparsity penalty here, and that basically ensures that each of those components that I learn is sparse. Because these weights are actually, think of these weights as, sparse images, but I put a penalty on this weight, so then lots of these images will be sparse. So it will do some components, learn those components here. Okay. Typically, we use mean squared error for loss, but we also, binary cross entropy also works very well. You can normalize all the feature to between 0 and 1, and once you do that, you can use simply binary cross entropy loss also, right, for the loss that we use. So both the losses work well on autoencoders. Okay, here is a real example. MNIST we talk about. So your input size is 28 cross 28 images, so that gives you a dimension of 784. And you put it in this network, learn an output, which is again of the same size. Okay. And it's a simple architecture. This has, standard activation. This is not a linear encoder. And you have, 784 and 8 hidden layers. So from 784 you go to 8 representation layers and back to 781. And here are the results with 16. And here are the results with 64. So here what you see is the digits that you present to the autoencoder. And here what you see is the reconstruction done by the digits. So 8 is not quite great because you can see some digits are not getting represented properly. But if you come to, let's say, 16 or even 64, then you can see almost perfect representation. Okay. And here are the results that are comparing original images with the cross entropy loss, autoencoder trained on cross entropy loss, and an autoencoder trained with the mean squared error. And you can see both of them are performing reasonably well in terms of representing this image in a smaller dimension. Okay. Any questions on this so far?
So this class autoencoders, does it increase the size of
It doesn't have to, but you can consider a class of sparse autoencoders that can also increase the size of the input. That's also possible. But the representation will still be sparse. So your Zi will have a lots of zeros. So your space, the feature space is very large, but number of non-zeros in Zi's would be still much smaller than n, the input feature size. Okay. So the other class of autoencoders are what are called denoising autoencoders. So you're given an image, and let's say we want to have a latent representation inside, and then reconstruct the image in a way that maybe the image has a lot of noise, and I want to remove the noise in the image. So what do? I take my input here, that could be the input image, and I add some kind of random noise to the image, and I feed that to my encoder. So I got a corrupt input now, an image which is corrupted by the noise. I represent it in low dimension. Now I can think of this image as the essential features of the image, right? Let's say image has a face in it, or it has an animal in it. So that's the essential feature of the image. Plus it has a lot of noise. So the noise is something that we don't want to represent in low dimension. We only want to keep the features in the low dimension. So then there's a decoder layer. I get my Y as the output. Now my loss function is not the input that I gave to the autoencoder. My loss function is the actual input, the uncorrupted image. Right? So this is Xi. This is Xi plus Ei. This is error. And I get my output from the autoencoder. And my loss function is difference between Xi and Yi. So now what this autoencoder will learn is also learn the characteristics of the noise and learn to drop it, and characteristics of the real images and learn to keep that in the low dimensional representation. And with this we can train an autoencoder that can denoise an image. So given an image which has a noise, you can learn to remove the noise in the image. Here are the results. There is a data set called MNIST fashion MNIST, and again it is 28 cross 28. And again in the test set, if you give original images with the noises, this is what you will feed to the autoencoders, and you can see the reconstruction that comes out actually denoises these images. Very nice. And these are very simple codes. I can point you to the notebooks. You can experiment yourself with these codes. I think these would be, very interesting to experiment with. Okay. Do you want to experiment with this? Should we give a homework on this? Simple homework? Okay, we'll try. We'll make something. Contractive autoencoders. Essentially here the idea is, I'm sort of just giving you a very, very high level overview here. The basic idea is that you want to sort of have the features that you learned inside the autoencoders, they should be less sensitive to the small changes in the input Xis. So you can define a term j comma u as the rate of change of the input unit, the unit output of the unit u with respect to the input j. Right? So that's a derivative. It's sort of forward propagation derivatives, and not the back propagation derivative, but the forward rate of change of the activation with respect to the input. And then you can put a penalty on the L2 squared of this. So what will it do is the weights it will adjust the weight so that the input these activations are much more smoother, as they don't change very rapidly with respect to the input. Right? So it will make it much less sensitive to the noise. So does it really give us anything? So here is an image. You can see this is the real data again on the imaging data set. This is trained on a 30-dimensional deep autoencoder, and this is the reconstruction you get from a 30-dimensional deep autoencoder. And if you compare it with the similar representation, a PCA representation, 30 dimension, you can see that an autoencoders are doing much better job at representing these numbers. Right? So here what happens is you have a training data, you split it into training and test. With the training data you train the autoencoder, and then you take a test image and then you give it to the autoencoder and see what it does to it, right? And same with PCA. You have the training images, you do the PCA on the training, you find the latent representations, you find these, singular value matrices, and then for a new example, you project it into the low dimensional space and you reconstruct it back. So basically in the test data, okay? So autoencoders were, the idea has been there for quite some time, but they were not very well used in practice because of the difficulty in the training, especially the deep autoencoders. And the reason they were not very useful was because they were getting stuck in a bad local minima, right? They were not really getting good autoencoders if you just do conventional gradient descent. And for a long time, L1 based, were still okay, but again, they were not as good as the autoencoders that we have today. And this is one of the breakthrough, papers that showed how to train the autoencoders. And they call it layer by layer training using what is called a restricted Boltzmann machine. And they use, so what they basically do is, they construct, similar to the autoencoder, they construct what is called a restricted Boltzmann machine. So they binarize the inputs and outputs, and based on that they learn the weights of what are called as a restricted Boltzmann machine. I'll just talk about it very briefly in a minute. But once they learn these weights, then they learn it layer by layer. So what do I mean by this? Okay, so essentially, yes, by doing this, they could actually train good autoencoders. So what they said was this process, if you use those as the initial weights, then you can get good autoencoders. So, and they claim that it seems to work well. Okay. So, what is it? What is a restricted Boltzmann machine? It is what is called a latent variable model. I'm sorry, I'm going a little fast here, but we're not getting into too much details here. But what is a latent variable model? So far we talked about a discriminative model, right? So what is a discriminative model? So I've given xi's and yi's. My task is to predict yi. Okay? In other words, so basically what I do, how do I predict yi? I have a model, and using that I come up with some yi hat. And yi hat is, let's say yi is binary, 0 or 1. So my yi hat is between 0 and 1. It's a number between 0 and 1. So in other words, it's a model for probability of yi given xi. That's a discriminative model. So I've given the feature vectors. What is the probability that my yi is 1, or what is the probability my yi is 0? So if you model it as a probability function, my discriminative model is actually trying to approximate this probability distribution using the neural network that I have trained. So using this neural network, I get a yi hat, and that's my model. That's my pyi given xi. What is a latent variable model? Now, in latent variable model, I don't have yi's. I only have xi's. Right? So, I only have xi's. But what I say is these xi's have certain, xi is a feature vector. I've got a bunch of these examples. They are from some distributions. And these distributions have some inherent properties. Okay? And those inherent properties I'm going to represent using Zi. So, xi has and this is represented using Zi's. So, in other words, what I'm saying that I have a probability distribution over xi and zi. And zi's are my hidden variables. So I'm learning a probability distribution. I'm given xi's. My probabilistic model is a model of xi, which is known, a known variable, but a latent or a hidden variable, which I don't know. And I'm learning the probability distribution of xi and zi. Once I learn this distribution, I can find what my zi is given xi, and what given zi, I can find xi as well. So I can go both ways, from xi to zi to xi. Okay. So one such example could be, you can think of an autoencoder, right? I have given the input, I'm learning a latent representation in the low dimensional space, and whatever neural network I learn, you can think of it as it's a model that I learned from xi to zi. Right? Another example, I can look at a simple example. Let's say I'm sampling the height of people in IIT. Right? So let's say my xi is the height of the ith person. Okay. So again, when I'm building a model for probability of xi or probability of x, I can say that this model has, some kind of distribution, maybe a Gaussian distribution with some mean mu and some variance sigma squared, right? But let's say it is a mixture of two Gaussians. Okay? So you are given, let's say, sample of heights of people, and let's say mu1 is the mean height if the person is a male, and mu2 is the mean height if the person is female. And the heights are Gaussianly distributed along the mu1s and mu2s, depending on whether the person is a male or a female. So now the height distribution of each person is a mixture of two Gaussians. Okay? And the first Gaussian has a mean mu1, the second Gaussian has a mean mu2. Now if I only gave you the samples of the heights, then you cannot figure out what are my probability parameters mu1 and mu2 that easily. Okay? But if I also gave you the latent variable here in this case is the gender of the person. So if I gave you the latent variable along with the height of the person, then you can club all the observations of males on one side and model it as a Gaussian distribution and just calculate the mean, and that will give you mu1. Similarly, all the females, that will give you mu2. So this is an example of another latent variable models where you have not the complete information, some information, but now with just the partial information xi, I want to learn a mixture of two Gaussians. So I want to learn P of x comma z. In other words, I want to learn mu1, mu2, sigma 1 squared, sigma 2 squared without knowing z. Right? So that's the latent variable model. Right? And that happens, this kind of model happens very frequently in machine learning, especially in many of the deep learning models, we see a lot of these latent variable models. So Boltzmann machine are a similar, latent variable models. So again, this is the input I have, some d-dimensional space, and these hidden variables are the latent variables which are in much smaller dimensional space that we don't observe, but the model assumes some distributions. And these lines here mean actually dependence relationships. So if this variable depends on this variable, they are probabilistically dependent on each other, then I put a line between them. And what restricted Boltzmann machine does is it removes the lines or dependence between the inputs directly. So essentially what it says is that these are the input variables. We have got some d dimensional here, but m dimensional in general. And there's some hidden variables here, and they depend upon this through some weight vector w. So when I write h equal to w transpose input, essentially my output h is actually dependent on the input according to these weight vectors. But these vectors are binary, so we're not going into details. If maybe at some stage we can cover restricted Boltzmann machine in more detail, but that's the basic idea of RBMs. So this is very similar to what we have in the case of autoencoders, right? We start with this vector we go to the next layer of hidden variables. The only difference is that it's a statistical model, and my input and the outputs are binary. So these are with these two differences. So what Hinton does is gives you a method to train a deep autoencoder. And what his method is that here is your input. Let's say it's an image, and then through some weights it reduces it to 2000 dimensional space. Now this he feeds it to what is called a restricted Boltzmann machine and reduces it to 1000 dimensional feature space. And this RBM, there are methods of learning that RBM. He learns that RBM and learns these weights. Then again it feeds this 1000 into another RBM to 500. And then from here to here it goes to a 30-dimensional representation. So each of these RBMs are trained separately and individually. Then he creates this autoencoder using the same structure, same architecture. And he initializes these weights in these architectures exactly as the weights he has learned in the RBMs here at each layer. So this is what we call layer by layer training of the deep autoencoder. And the weights in the decoder are just the initialized to the transpose of the weights of the corresponding autoencoder layer. And then you finally get the output. So this is what they call unrolling. So now you have a bunch of image inputs. You create a deep network, but you don't start learning a deep network right away, because if you just do random weight initializations, you'll get stuck in a local minima, and that will be a problem. So what you do is you train these individual RBMs for each layer separately, and whatever weights you get, you feed that onto the autoencoder here, use that as the initial weights, and now you train your autoencoder with these initial weights and carefully. And this, he says, gives you a very good way of training the autoencoders, which can do something useful. Yeah.
What's the data for training any individual layer?
Same as your. So here, for example, in this layer, you will train on the input faces. Here the data is faces. Now, after this has been trained, you will get, for each face, you will get a 2000 dimensional vector. So the next layer, those vectors will be a training.
We don't have any corresponding 1000 dimensional examples. How would we train them?
This is unsupervised. This is RBM unsupervised. I have not told you how to train the RBMs. I have just given you a very high level idea of RBMs. But just the way we train the autoencoders, right? There is a way to train the RBMs as well. You look at some energy function and you minimize that function, so somehow, that's not going there. But basic idea is through these RBMs you will get these weight vectors, and that's what you use for initialization of your deep autoencoder, and use that to reconstruct.
So these latent variables are basically describing our probability distribution of the data, right?
Yeah, of the input basically, yeah. So again, to see the results, this is the input given, and this is a 6-dimensional autoencoder. What does it mean? That in the final layer of the autoencoder, you only have 6 units. And then if you do a PCA, there is a variant of PCA, logistic PCA, 6-dimensional, 18-dimensional, standard PCA. You can see that it hugely outperforms the PCA. Even with 18 dimensions, the 6-dimensional autoencoder is doing much better. Okay. This is on the MNIST data set. If this is the input you give to autoencoder with 30 dimensions in the final layer, and then you do logistic PCA and PCA with 30 dimensions, you can again see that the kind of, the quality of the images that you get is much better with the autoencoder. Okay. Now, you can also apply it for documents, right, for text processing. So let's say I want to find documents which are similar to a query document. I give a document and then give me all the documents that are talking about. So for example, I'm looking at the legal judgments. So I have a corpus of judgments, and the arguments there. And then I have a new case that has come in. I formulate this, describe the case properties and put it as a document. Give me all the judgments that are similar to this. So that kind of problems can happen. So the documents are converted into bag of words, and for each word, they're encoded as a feature vector that gives you how many times that word comes in. Okay? And they are using 2000 words. They have selected 2000 words for encoding instead of a dictionary of millions of words, just restricted to 2000 words. And then an autoencoder that compresses it to 10 dimensions, and then back to full 2000 dimensional space. Okay? So this data is trained on 4 lakh business documents, and these documents were hand labeled as belonging to different categories. So there could be legal, there could be news, entertainment, and so on. There were multiple categories, they were hand labeled. And then they did this. So once you have an autoencoder, then you look at document and then look at fetch the related documents, the documents which are closer to that, similar to that document. And what you find is with just 10 dimensional representation, it is doing as good as what is called the latent semantic analysis with 50 dimensions. This is essentially a variant of a PCA. Right? It's doing better than that also. And with 10 dimensional PCA, it's doing significantly better. But if you further develop the autoencoder and take it down to 2 dimensions, so you take this 2000 dimension feature vector, compress it to 10, further compress it to only 2 dimensions. Then what happens? Now you do PCA. So you take these documents, put it in 2 dimensions, PCA. Now these different dots, the color, each dot is a document, and the color of dot represents the class to which it belongs. So PCA is unsupervised. We don't give the class labels to PCA. So you can see there is a bit of separation here. Greenish is here, the bluish is here, right? If you do PCA. Because PCA is limited by making sure that it is linear. But same data, if you do autoencoders, you can see how nicely the classes have been separated out. So the government borrowings, which are represented by dark green, all these documents are in this 2-dimensional space. So just in 2-dimensional representation, you can have a very nice, representation of these documents. Okay? I'll just very quickly talk about variational autoencoders, because those are the most popular autoencoders that are used, and they are most successful. And the basic idea here is, instead of mapping x to z via a deterministic function, I'll actually map it to a probability distribution. So my f is going to give me a probability distribution. And similarly, when I map from z back to y, I'm not going to map it deterministically, I'm going to get a probability distribution. And typical distributions are multivariate Gaussian, which means that when I'm encoding f to z, I only have to characterize that distribution. So I give the mean and I give the variance of that distribution. Okay? So these are what are called the variational autoencoders. So again, you have the input image, you encode it in a low dimensional representation. You only need the mean and the variance in the low dimensions. And then you sample from this. Now you have a low dimensional representation. So while reconstructing for this image, you can reconstruct multiple images, because now it's no longer a deterministic function. So once I know the distribution of z here, I can sample and can get different z's, and through this I can get different reconstructed images. Okay. So the loss also uses what is called a KL divergence plus the classical reconstruction loss. We're not going to the details there, but they perform really, really well. And some of the deep fakes actually use variational autoencoders to generate the data. And since it's a statistical model, it can also be used for generative modeling. Okay. So I'll stop here. I'll stop here, and then we'll take it forward in the next class. Okay? Thank you.